Okay, hello everybody. We are going to look at the basics related to chemistry in this session. So, our aim obviously is to cover all the topics that are related to NSEJS. Of course, it's a very wide topic to be honest. I mean, if you go through the syllabus, it looks like, yeah, defined as something that is still 10 standard. But obviously, the depth of knowledge you will need to have so that you can give this test very easily, that is definitely more than 10th level knowledge, if you ask me. Because it's a very competitive examination and the topmost bright students get selected eventually for the camp and all. So it's expected. But yeah, so at this level, when we are starting right now, because you viewers could be in eighth, ninth, some are even very enthusiastic seventh standard students. So seventh, eighth, ninth, tenth, everybody should understand. So at that level is how we have to go ahead with this topic, right? Of course, at this point, what I'm going to do is we'll go really slow because in the beginning you have to understand things really well. Once you have built up your base, maybe we can take things up a bit more faster or so that we can cover the whole portion. To be honest, it's like almost as good as JEE syllabus. Maybe a few chapters are missing out here. Other than that, most of them are there here, right? So, where we start with is normally with mole concept, the idea of mole, the idea of quantitative chemistry. So the way chemistry is taught, the way things are taught in general is how you get to know the basics first, you kind of build up on them slowly. So in chemistry, the way we go is to start with the idea of mole. How do we count in chemistry? How do we quantify things? Because eventually anything that we deal with further down in chemistry is also going to be much more easy to handle if our clarity about quantity is clear, right? So, as far as quantitative chemistry is concerned, the most fundamental things we need is the idea of what you call as mole, right? But yeah, I mean, of course, we could always just like go ahead in the conventional way where we say, okay, this is mole, this is a number, blah, blah, blah. But instead, what I prefer to generally teach a batch which is trying to understand things from basics is to go in a different direction. Why do we need mole? From there, we'll eventually understand what is this mole number all about and how do we count in chemistry, right? So, so before I go into mole, basically what I want to talk about is atoms in general, right? So of course, even before we speak about atoms, I should be speaking about what you call as subatomic particles and probably even like a little bit about fundamental particles. Although we don't need to have a lot of knowledge about any fundamental particle at this point. Now, what do you mean by a fundamental particle? Fundamental particle is if you cannot further subdivide this into something else, then it's called a fundamental particle, right? Absolutely smallest building block of whatever, right? So as science stands right now, there are many fundamental particles that we speak about 17, I guess. Standard model of science speaks about 17 fundamental particles, of which like many students have a very basic misconception that protons and neutrons are also fundamental particles, while they are not, right? They are subatomic basic building units of an atom. So if you think about an atom, you have your nucleus, which is protons and neutrons, and you have your electrons revolving around them. So they are the subatomic particles, right? But they are not fundamental protons and neutrons, right? Electrons are fundamental particles called electrons. But yeah, as far as protons and neutrons are concerned, they are not fundamental. They can be further subdivided into different quarks and all, right? So quarks held together by gluons. But yeah, as it stands, these fundamental particles individually might or might not have a solid existence of their own. So, as far as atoms are concerned, what we know of as the visible universe, what we know of as things that we have seen and known all our life and stuff like that, they are made up of atoms. Right? Atoms are the smallest particles that we can think of. Dalton's atomic theory speaks of what he calls as atoms as the smallest indivisible particles and so on. And we say that atoms combine in simple whole number ratios to make up molecules and then eventually stuff like that, right? So I'm not going to details of Dalton's atomic theory and all. I'm pretty sure you have heard of this and you've seen the counter arguments against it, how atoms are not the smallest. There are, like, they are made up of protons and neutrons in the nucleus, and the electrons and all, subatomic particles discovery and all. We'll be dealing with all of that as well. Although, I mean, in atomic structure, we'll be dealing with all of them in a different way about the history behind all of them. But here in this chapter, mole, because we are going to define a term called mole, just like how we have a dozen as 12. We'll define something called as a mole, which helps us in counting or expressing quantity in chemistry very easily, right? But as I said, before we go into mole, we need to understand why we need this mole thing. For that, I'm going to start from atoms, right? So, yeah, as far as atoms are concerned, as I told you, we have what you call as a nucleus, right? Which is basically your protons plus neutrons, right? And we have what we call as the electrons, right? So these are the things that you can broadly say as the things that are there in an atom, right? So you have your protons and neutrons, which make up your nucleus, and you have electrons around them, right? Where are they? What are orbits that Bohr spoke of? What are orbitals that we have in, like, what you call as the quantum wave mechanical model of the atom? All of these things will come to later on in atomic structure chapter. But yeah, we know on a very simplified, oversimplified way, we can say that there is this positively charged nucleus and we have these electrons that are going around them, right? So as far as these electrons are concerned, these are negatively charged subatomic particles. Of course, the sizes are all drawn here and all are very misleading. Nucleus is infinitesimally small, very, very, very small, and the electrons are like revolving around them in huge regions, right? Making a vertical as the size of the atom. But yeah, that's a different story. As I told you, atomic structure, we'll eventually come back to that. But yeah, point is, as far as an atom is concerned, it consists of this positively charged nucleus, right? Which has your protons and neutrons, okay? Protons and neutrons. And then you have these electrons around them, build making up your atom, right? So if I speak about quantity, it's about mass. I'm trying to quantify. I mean, how do we speak about something? Like, let's say if you have a gas, you could speak in terms of volume. Liquids and all, you could speak in terms of volume. Mass is obviously always there. So gas or solid or liquid or whatever you have, it has a mass. As long as something is matter, it has atoms, and atoms have a mass. And you can think about mass as a very easy way to communicate about quantity of any substance we have, right? So as far as the atom is concerned, if I'm speaking about the mass of an atom, right? So let's say that I want to speak about the mass of an atom. I can say that it will be equal to the mass of protons plus neutrons plus electrons, right? This should tell us about the mass of the atom. All of these masses combined, you have your protons, you have your neutrons, you have your electrons. All of these combined, they have some mass. That will be the mass of your atom if there is nothing else in there, right? So obvious, like for example, let's say I have something like helium, let's say, right? So helium 24 isotope, right? What do you mean by an isotope? Same atomic number, different mass numbers. I'm pretty sure you have already heard about this. But yeah, so let's say I have helium 4 nucleus with me, or helium 4 atom instead with me, right? So this has two protons, two neutrons, and two electrons, right? So this is what it has. So the mass of your helium atom should be the sum of all of these, right? Uh, Answer is kind of yes as well as no. But yeah, what do I mean? We'll see as we go forward, right? So of course, the sum of all of these is roughly going to be the mass of your atom. That is obvious, right? What do I mean by approximately the mass of the atom? That we'll see as we go forward. But the idea is, these are the three things that are there inside your helium atom. So the sum of all of these masses should give me the mass of your helium atom, technically, right? So when I'm looking at a proton, right? So proton, to be honest, as well as your neutron, roughly has a mass of around 1.67 into 10 to the power minus 27 kg. Right? So this is roughly the mass of one proton. Similar is the mass of your neutron. Neutron is slightly heavier than your proton, but yeah, almost the same mass is what it has, right? And now, as far as your electron is concerned, right? Electron is much lighter, and electron has a mass of approximately 9.1 into 10 to the power minus 31 kg. So this is obviously, as you can see, like from the 10 to the power minus 27, we can see that this proton neutron is also very, very, very tiny, very small mass. And on top of that, you can see that the electron is even lighter, much more lighter, about 1840 times lighter compared to your proton, right? So say that I'm trying to find out the mass of your helium atom, which is roughly sum of all of these. So can I say that, okay, your mass of atom. Wait. Hmm. Right. So yeah. So let's say that mass of helium atom is what I was worrying about, or I'm trying to speak about. So let's say that the mass of your helium atom, helium 4 atom, will be 2 times mass of your proton plus 2 times mass of your neutron plus 2 times mass of your electron. Right? MP, Mn, and Me I'm using for the mass of your proton, mass of your neutron, and mass of your electron. Right? So these three are what I'm adding to get the mass of your atom, out of which these two are significant. This is kind of insignificant because you can see mass of your electron is way lighter. So I can kind of ignore the mass of an electron when I'm speaking about the mass of your helium atom, right? So I can say that this is approximately 2 times mass of a proton plus 2 times mass of a neutron, because this is anyways very, very small. This is kind of negligible, right? So I can say that mass of your atom will be something like this helium atom, right? Specifically helium 4. So this mass of your proton and mass of a neutron also, I told you, they are approximately the same, right? So when I'm looking at this, both of these are approximately the same. 1.672 into 10 to the power minus 27, 1.675 into 10 to the power minus 27, something of this sort. So they are approximately the same. So these both are what you call as your nucleons, right? The particles that are made making up your nucleus, these are called your nucleons. Protons and neutrons are called your nucleons. Now, if their masses are approximately the same, why speak of them separately, right? I mean, let's just put a new symbol for both of these so that it gets a bit more convenient. So let's say that this is approximately 4 times the mass of a nucleon. What is this Nu? Mass of a nucleon, which is your proton or neutron mass, which is approximately the same. Obviously, it's not a single value, but I'm just saying that let's say that they are approximately the same. Let me put a new symbol for it, mass of your nucleon, right? Now, before we go into mole, we are going to look at some other definitions as well in this session. Right? These are all very fundamental, very basic things that you have to know before we go any further. Right? So this is approximately the mass of your helium atom. Right? Whenever we speak about any physical quantity, right? Let's say that this mass of a nucleon is 1.67 into 10 to the power minus 27. So I could say that mass of your helium atom is approximately 4 into 1.67 into 10 to the power minus 27 kg. This is what it is, right? Because kilogram, if you want to speak kilogram as the unit for this, of course, you can see this is a very small number, right? So let's say that you're speaking about any physical quantity, like for example, your height or your weight, right? Let's say that we are speaking about height. Then we say, okay, height is probably, let's say 160 centimeter. I don't know how tall you are at this point, but yeah, let's just say it is 160 centimeters. Okay? So you could say 160 centimeters, you could say 1.6 meter. It would mean the same thing, right? Or you could have said like something like 1,600 millimeters or whatever. It would still mean the same thing, right? But yeah, notice that I would probably pick up something like this or this, centimeters or meters, because the communication bit gets a bit more realistic or easy to visualize, right? So if I'm saying 160, oh, you're like, yeah, fine, okay, 160, decently large number. I can't obviously show it in my fingers, but yeah, okay, understandable, relatable. 1.6, maybe even more so, right? So it's like, of course, decimal, thinking in decimal, but yeah, it's like 1 meter, 2 meter, somewhere in the middle of that, you will be having this 1.6 meters, right? So easy to visualize. But if I use kilometer as my unit, right? So kilometer, this would be what, 0.0016. Yeah, this doesn't make any sense, right? I mean, when you're thinking about the length of a human body, a length of the height of a human being, obviously you wouldn't visualize it in kilometers, right? That is a significantly larger unit for this, right? Doesn't make any sense. It's like 0.0016. Why would I want to speak in a unit where my number is so senseless, right? So this becomes very cumbersome, right? This becomes a bit more difficult to communicate. So, my point being, what I'm trying to arrive at is, whenever we speak of a physical quantity, we try to pick up a unit which makes the communication a bit more legible, easier, and easier to visualize, right? So, I mean, if I'm speaking about the mass of my helium atom, right? So we saw that the mass expression was 4 times mass of a nucleon, which is approximately 4 into 1.67 into 10 to the power minus 27 kg. Imagine, is kilogram the good unit when you are speaking about mass of one atom? A larger quantity, of course, would be different, but because just speaking about one atom, kilogram is definitely not the best unit, right? So this 4 into 1.67 will be roughly how much? 1.6 into 4 is 6.4. Around maybe somewhere around 6.6, 6.7 into 10 to the power minus 27, which means it's 0.00000 as it 26 times. Then you have your 6, 7, whatever. That doesn't make any sense. Even like a 2 0 that I saw in this is making me uncomfortable. Imagine using a unit where, I mean, imagine using something like light year to speak about the height of a friend, right? So this guy is like 1.1 into 10 to the power minus 29 times light year. That doesn't make any sense, right? So, I mean, of course, I don't know the exact number, but yeah, it doesn't make any sense to speak in terms of light years for height of a human being. Similarly, it doesn't make any sense to use kilogram as the unit for mass when you're speaking about mass of an atom, right? So we need a better unit, right? I'm pretty sure you have already guessed what we are talking about. I mean, what I'm trying to arrive at. I'm trying to arrive at what you call as AMU, right? Atomic mass unit. What is the definition? We'll come to that. But yeah, the need, I hope, is clear, right? So the need is, obviously I can't speak in terms of kilograms when I'm speaking about mass of an atom. I need a much more smaller, more convenient unit, right? So point is, I mean, we were speaking specifically about helium 4 nucleus right now, but let's speak about another atom for the time being. Let's say we have a general atom XZA, right? So what is this? The general representation, right? General representation of an atom, representation of an element, to be honest. But yeah, this is the general representation of a nuclide, if you want to maybe speak of that, right? So where this, what is this X? X is the symbol of the element, right? Like how we had helium 2 4, I had written like that. So 2 was the atomic number in helium, right? The number of protons, and 4 was the mass number, which was protons plus neutrons, right? So He24, just like that we have an XZA, right? So what does this mean? Here we have Z protons and A minus Z neutrons. A is the mass number, which is neutrons plus protons. So A minus Z is going to give me number of neutrons, right? So protons, and of course, if there are Z protons and you're speaking about a neutral atom, there will also be Z electrons. Right now, this is what it is there, but let's just say that we want to say, okay, this Z is like your P, right? Number of protons. This A minus Z, let's say, is N, the number of neutrons, right? So Z is P. I'm saying that there are basically P protons, N neutrons. It's a bit more convenient instead of saying Z and A minus Z and all that. No? So let's just say there are P protons, right? And there are N neutrons, right? Of course, in the neutral atom, you will also have P electrons. But yeah, we have already established that when I'm speaking about mass of an atom, we can ignore electrons because they are way too light. So yeah, we can say that mass of an atom will be equal to mass of an atom of X will be equal to P times protons, mass of a proton, plus N times mass of a neutron. Right? P times mass of a proton plus N times mass of a neutron. Of course, this is not what it is exactly equal. Of course, we can say this is approximate. There are multiple reasons for this, not just because the mass of electrons we have kind of ignored. There are other reasons also why this is not exactly equal, right? We'll come to that. We'll come to that shortly. But yeah, the idea here is mass of your atom will be approximately P times the mass of one proton and N times mass of one neutron because there are N neutrons and P protons. Like in helium, example that we saw, P was 2, so 2 into mass of a proton, and N was also 2, so 2 into mass of a neutron. So we had our this thing, right? Mass of your helium atom as 4 times mass of a nucleon. Like that, can I say that this is approximately P plus N times mass of a nucleon? Because MP, Mn, both of these are approximately equal, and instead of these, I can put mass of a nucleon. So I can say that mass of an atom is approximately P plus N times mass of a nucleon, right? So like in our helium, for example, we had P plus N as 4, so 4 times mass of a nucleon is what we got in helium, right? Just like that, we can say for a general atom, whatever is the mass number into mass of nucleon will give me mass of my atom, right? Let me, for example, write maybe something like, let's say if I have something like sodium, which is 1123, let's say, right? I have sodium 1123. So here I have 11 protons and I have 12 neutrons. So your mass will be approximately 23 times mass of a nucleon. This is what we are saying. N plus P times mass of a nucleon will be the mass of one atom, right? Mass of your atom. Of course, if I try to calculate this, we will see that this becomes, this will be equal to how much? 23 into 1.67 into 10 to the power minus 27 kg or minus 24 grams. But this is very, very small a number, right? That was our concern. So we were like, okay, we need a better unit, a smaller unit, so that my communication about quantity, mass of atom is simpler to communicate, right? So the point is, as you can see, this multiplication of mass of nucleon is what is actually making it a tiny number, no, in kilograms, right? So mass of your nucleon, mass of your neutron and proton is very, very small in kilogram units. But what if this is my unit? What if this was my unit? Then my number would be easier. No, then it will be 123 units. This is so much more convenient, right? So that is the reason why we are like, okay, this can be made simple if I could define mass of a nucleon as my unit, mass of your proton or mass of your neutron as a unit, then my communication gets really simple, right? This is the idea from where we begin, where we say that, okay, let me define AMU as 1 by 12. Although, yeah, this definition and all are not there right now, strictly speaking. But yeah, the way we define it for our syllabus is AMU is 1/12 the mass of a C12 atom, carbon 12 atom. 1/12 times the mass of a carbon 12 atom. So what is happening here? Let's see this mass of carbon 12 a little bit more in detail. So carbon 12 would mean that I have C612, which means I have 6 protons and 6 neutrons, and of course 6 electrons in the atom. So if I'm speaking about mass of carbon 12 atom, mass of atom, this will be approximately what? 12 times mass of a nucleon, right? So this is, or you can say that this was 6 times mass of a proton plus 6 times mass of a neutron. Approximately, this is where we started. But yeah, this is what we have, right? So if I do 1/12 of the mass of this atom, right? So that was the definition. So what am I doing? 1/12 times mass of your C12 would mean that I have 12 times mass of a nucleon approximately. So this is equal to mass of a nucleon. So this is the aim. So this is how we define it as 1/12 of the mass of a carbon 12 atom, so that I get that mass of a nucleon, average mass of a nucleon. This I can now use as the unit to communicate mass of every atom. Then it should have a mass which is like very easy to express, like how sodium could be expressed as 23 units, carbon can be expressed as 12 units, nitrogen can be expressed as 14 units for that isotope, oxygen 16 units, and so on, right? So this is the fundamental idea. What did we do? We are like, okay, we need a better unit. The best would be mass of a nucleon, because that is the small number which is making all my calculations really ugly, and this is giving me like these very small numbers. Let me use a better unit, right? That was our whole aim. So we have defined AMU as 1/12 the mass of a carbon 12 atom. Of course, it could be anything. You could roughly say it is mass of hydrogen atom, because hydrogen atom is what? Proton, electron. Protein, I mean hydrogen 1 isotope. So you have 1 proton, 1 electron. Mass is approximately 1 proton, which is a nucleon. So yeah, you could say it is hydrogen atom's mass. You could say that it is 1/4 times mass of your helium. We saw 4 times mass of a nucleon roughly, right? So 1/4 times mass of helium, or after that you have your, let's say, sulfur 32. So 1/32 times mass of a sulfur atom. We could define it in any way we want, right? But yeah, this is how we defined it, right? So 1/12 the mass of a carbon 12 atom. Now, obviously, if this is the average mass of all the protons and neutrons that are there in carbon, shouldn't this be approximately equal to the mass of proton and neutron, which is 1.67 into 10 to the power minus 27? Answer is yeah, we would have expected it to be, but yeah, 1 AMU is actually 1.66 into 10 to the power minus 27. This is slightly smaller. How is this even smaller? I mean, if there are 6 protons, 6 neutrons, and 6 electrons in a carbon 12, and if I'm dividing it by 12, shouldn't the mass be somewhere close to mass of a proton at least? I mean, between proton neutron maybe, but at least a proton. But this is actually even less than that. So the reason here for that is something called as mass defect, right? Or nuclear binding energy. The point is, we'll deal with in detail when we go into nuclear chemistry as a part of chemical kinetics. But yeah, point here is, when you are keeping all of these protons together, right? So protons repel each other. They have electrostatic repulsion, right? So they are positively charged objects. They repel each other. How is it that I'm putting all of these protons and neutrons in one place? Right? The neutrons are neutral, of course. They don't interfere in this electrostatic force per se. But how are these protons, which are going to repel each other, kept in this small region, right? So we know nucleus is roughly of the order of 10 to the power minus 15 meter, right? Femtometer or Fermi, right? So this is a very tiny region, and you're putting all of these protons together. Won't they repel each other? Of course they will, right? In order to overcome that repulsive electrostatic force, there is another force that like kind of counters in, which is called the nuclear binding force, right? Nuclear binding energy is involved here. So the point is that we when we are forming a nucleus which has more than one protons, unlike hydrogen doesn't have this case. So yeah, because it's only one proton, what will it repel, right? So hydrogen per se is the place where you don't have this repulsion, but in others, this repulsion is kind of overcome by another category of force altogether, right? Which is your nuclear binding forces, right? So as far as these binding forces are concerned, how do they come into picture, and all of this is a much more elaborate topic of discussion which we don't want to go into right now. But the idea is, whenever you release energy, right, so things become more stable, right? So gravity was acting on this force was acting on this, it is pulling it closer to earth, and as you get closer, there is a reduction in energy in the system. If you can hear it, I'm not very sure you can. Even this small, from this small height, when I'm dropping this pen, there is a sound that is released. All of that sound energy, where is that coming from? That is the energy lost when I'm dropping it. So I'm picking it up, I'm doing work to put this increased energy in the system. I'm dropping it, it goes down, that energy is released, some amount of vibration and all, is how the energy is dissipated. But the point is, reduction in energy kind of stabilizes systems, right? So as far as energy reduction is concerned, some amount of mass is lost from the system, right? Which is called the mass defect, delta n. When you have your protons being close together, and along with neutrons, like kind of acting like glue for them, when these nuclei are built, some amount of mass is lost from the system in the form of energy, nuclear binding energy, which kind of keeps them together, right? So some amount of mass is lost from the system, and that is the reason why when I'm taking carbon, right, when I'm doing 1 by 12th of mass of a carbon 12 atom, I'm getting a value which is slightly less than the mass of a proton as well, which is, we didn't expect this, because 6 times mass of a proton plus 6 times mass of a neutron would mean at least 12 times mass of a proton. So dividing that by 12, plus you have 6 electrons as well, but for the time being, let's ignore the electrons because they are very light. Even then, at least 12 times mass of a proton is what I would have expected carbon's mass to be. So dividing it by 12, I would have expected at least mass of proton, but I'm getting something slightly smaller than that because of this mass difference. Right? But yeah, whatever. We had to define it some way or the other. Hydrogen couldn't be used as the yardstick anymore. You can understand why. Because if I use hydrogen doesn't have mass defect. So mass of your proton is higher than mass of the average mass of nucleons in other atoms. So the idea is using hydrogen would not be the best. So we define carbon. I mean, we use carbon as a yardstick to define what you call as the AMU, right? Our unit for mass on a very subatomic level, right? On a tiny level. So that my communication about mass of atom gets more legible and easier, right? So yeah, this is how we define AMU, right? Now, of course, if I want to speak about mass of your helium, I could now say it is 4 AMU, or like let's say nitrogen, I could say it is 14 AMU. Sodium, I can say it is approximately 23 AMU. All of these are not exactly equal, because you can understand each of these atoms will have different kind of mass defects, based on how many protons have to be held together and how many neutrons are there and all that. So obviously we don't control the exact values of these masses of individual nucleons in every element, but yeah, we can all say they are approximately close to this, right? Now, so we have defined AMU, right? We have not reached mole yet, but yeah, we have defined what we call as AMU. So AMU is a small unit which we use for mass on a subatomic scale, which is approximately the mass of a nucleon. This much we are clear. We know its value as well, the calculated value based on taking like your carbon as the yardstick, we know, right? Now let's understand, why do we need this mole? Of course, when we are speaking about any quantity, like real life quantity, I am not going to deal with one atom, two atoms, 10 molecules, and stuff like that, right? What are molecules? Molecules are the smallest independently existing particles, right? So when I'm speaking about air, we have nitrogen, we have oxygen, majority is them. We have like krypton and all as well, argon and all as well. All of these other gases are also there, but primarily nitrogen, oxygen, right? In them, we have like N2 is the molecule of nitrogen, two atoms of nitrogen combined to each. We have O2 is the molecule of oxygen, two atoms of oxygen combined to each other. So whenever I'm speaking about any quantity of air, I'm definitely not talking about 10 molecules, 20 molecules and so. We are speaking about a large quantity, right? A real life quantity will always be significantly larger than just one molecule or two molecules. So I need a way to communicate the quantity of substance I have. Let's say I have a cylinder where I have oxygen. I want to speak about how much oxygen I have. Of course, weight is one way to speak about it. We already know weight is easy to communicate. Weight, you can say, oh, I have 16 grams oxygen. I have 32 gram oxygen. I have 3.2 kilograms of oxygen. I can speak about that very easily. Mass is always there. But we want another way to communicate as well, right? Quantity. Like for example, if I take like let's say I'm going to buy some coconuts and I'm like, okay, there are 20 coconuts that I want. Okay, that is one number. I could say that I need 1.5 kilogram coconuts, right? That is definitely another possibility. Mass is there, but counting is also there, right? So as far as counting is concerned, for coconuts and all, for mangoes, for bananas, I can do a counting that makes sense, realistic. But obviously, when I'm speaking about atoms and molecules and all, actual counting number would be very, very, very inconvenient, right? Because it's insanely huge numbers that we have. So let's say if I have 1 gram hydrogen, right? Let's say I have 1 gram hydrogen, or let's say 1 gram oxygen for that matter. So let's say I have 1 gram oxygen. How much oxygen do I have? I need to find out. Let's say, for example, right? So we know what you call as unitary method. One molecule of O2. What is the mass of one molecule of O2? O2, let's say I have what I have is oxygen 816, which means that I have 16 AMU, right? 16 U, unified mass, AMU, Dalton, these are all the same. Dalton, unified mass, AMU, all of these are the same. So let's say 16 U is the mass of one atom. Then obviously O2 would mean that I have 32 AMU. What is a molecule? Molecule is this two atoms combined. So if one molecule is 16 AMU, one atom is 16 AMU, two atoms or one molecule would mean I have 32 AMU, right? So one molecule of oxygen has a mass of 32 AMU, and let's say some N molecules, or let me put capital N molecules are there, which has a mass of 1 gram. Then obviously this n is going to be a large number. Let's see what this number is going to be. Unitary method, right? So you could cross multiply and you could get n is equal to n into 32u is equal to 1 into 1 gram. So n is equal to 1 gram divided by 32 AMU, right? Let's say like this. I mean, from what I've seen is that from teaching, whenever we speak about like atoms and molecules and all, where the masses are like very small and like kind of unimaginably small, it gets difficult for people to imagine. But let me put a simple example side by side so that it's easier to understand. Let's say that there are chocolates that I have, and each chocolate is like, let's say, 50 grams. Have these, let's say, chocolate bars, and each of them are 50 grams, and I'm like, I have 600 grams total. How many chocolates do I have? So you are like, okay, each chocolate is 50 gram. Total, this guy has 600 grams. So 600 divided by 50, which means that I have 12 chocolates. This is easy to understand, right? So just like that, I have 1 gram oxygen, and each of them has a mass of 32 AMU. So 1 gram the total divided by mass of 1, which is 32 AMU. This should be your answer. So this is 1 gram divided by 32 AMU was how much? 1.67 into 1.66 into 10 to the power minus 27 kilogram or 24 grams, right? So 32 into 1.66 into 10 to the power minus 24 grams. This is going to be the number, and gram cancels out, right? Or you could say that this is 32. Or strictly speaking, the mass of one atom, you could say that it is these many grams per atom, right? Or rather, this is not atom, no, this is molecule, right? This is the unit, you can say. Mass of one molecule. If I ask you what is the mass of one molecule, you can say 32 into 1.66 into 10 to the power minus 24 grams per molecule. This is how you could represent it. So of course gram cancels out, and this molecule will go to the numerator, and we'll have whatever this is, 1 divided by 32 into 1.66 into 10 to the power minus 24, these many molecules. So this you can see is a very small number, right? 1 divided by 32 into 1.66, roughly you can say is 5 by 3, right? If you want to simplify calculations. Now this 10 to the power minus 24, when it goes to the numerator. So you'll have 1 here and a 10 to the power 24 here. So you can see this is a huge number, right? So this, let me take this as roughly 10.6, and 10.6 into 5 is how much? 50 and 3, right? So roughly around 10 to the power 24 divided by 53. 100 by 53 into 10 to the power 22. This is a huge number, right? This is an insanely large number. So I have just 1 grams of oxygen, no doubt. But number wise, this is such a huge number. So I'm like, okay, let me use a better way to represent this number. Like I could say 12 chocolates, I could say 1 dozen chocolates, right? So that dozen is a way of simplifying my number. Like that, I'm saying, okay, if I want to speak about number of atoms or number of molecules, let me use a better unit, because actual number is going to be insanely large. Okay? So let me define a new quantity called mole. What is a mole? Mole is number of whatever quantity you have, if it has as many particles as there are atoms in 12 grams of a carbon 12 sample. Let me define that as mole. This is the definition of mole. Why? Because if you see here, so let me first deal with this number, and then we'll understand why this makes life so much simple for us, right? So if I'm looking at carbon 12, we know that carbon 12 mass of your carbon 12 atom was 12 AMU. Right? That is how we defined AMU. AMU was 1/12 the mass of a carbon 12. So mass of a carbon 12 will be 12 into AMU, right? And let's say that, so one atom is basically 12 AMU. How many atoms are there? Let me call it as Na. Why am I calling it as Na? This is basically Avogadro's number. So let's say Na atoms are present in 12 grams. So you can see cross multiplication. Na is 12 gram divided by 12 AMU, which is basically 1 gram by 1 AMU, which is approximately 6.02 into 10 to the power 23. Now, why is this convenient? Because everywhere, like for example, in this case, I had some weight divided by some number AMU, right? So there is this 1 gram by 1 AMU even here, no? This is the part which makes it a huge number. Other than that, what did I have? I had like 1 by 32. This is simple, right? So this is a small calculation, right? So this big number is your 1 gram by 1 AMU, which is going to be such a large number that I don't want to actually speak about this number. I want to represent it by a term mole. This is a huge number, right? So this is something that I can avoid whatever calculation I have, right? So for any substance, let's say that I have, let's say I have 24 grams of sulfur atoms, right? I mean, of course, I might not be having actual atoms. Atoms, they might be in the form of different types of molecules. Let's say I have crown sulfur, which is S8. But yeah, let's say that I have 32 grams, 24 grams of sulfur atoms. Sulfur 32, right? Sulfur 16, 32. So how many atoms do I have? Let's say somebody asked me this, how many atoms do I have? So I'm like, okay, one atom of sulfur has a mass of 32 AMU, right? And how many atoms are there in 24 grams? This is the question, right? So I want to find out this number, capital N. So I'm like, N is equal to 24 gram divided by 32 mu per atom. So this is equal to 24 by 32 into 1 gram by 1 mu atoms. This is the way it makes it simpler for us. This 1 gram by 1 AMU, I'm substituting it as Na, Avogadro's number, which is the defining number for mole. And the remaining calculation is anyways going to be simple. So this you can see is 3 by 4, right? 8 into 3 and 8 into 4. So this I can directly say as 3 by 4 moles. Whatever calculation I do, there will be some W grams divided by some AMU per molecule or per atom. So this gram by AMU calculation is always going to be there, which is what is going to make the number, final number, a huge number. I'm avoiding it by defining 1 gram by 1 AMU as Na, Avogadro's number, which is basically 1 mole, right? So the definition of mole is number of atoms in 1 gram, 12 grams of carbon 12 sample, which is same as saying 1 gram divided by 1 AMU, which is 6.022 into 10 to the power 23. This is a huge number, but yeah, actual quantity in any real life, actual number of molecules in any real life quantity, like 10 gram oxygen or 1 kilogram of oxygen, and all of these are going to be large numbers. So I'm simplifying my representation by using this new term called mole, which is just a simple counting quantity, counting term. It's defined as the that quantity of substance which has as many particles or entities as there are atoms in 12 grams of a carbon 12 sample. Cool. Let's end this session here. We'll solve some questions and all when we proceed in the class. It will make it more clear. But yeah, the definition. Why do we need this mole? Because we are trying to speak about number of particles, number of molecules and all, which is a huge number. So I want to simplify it by using another quantity, right? Which is what we have defined as mole. And before we went into the definition of mole, we looked at what we call as AMU, because anyways, these are like molecules and atoms that we are trying to deal with. So quantity of mass of one atom and all is also important before we understand this mole, because it's a weird number, 6.022 into 10 to the power 23. Why take this weird number? Why not just 10 to the power 24 or 10 to the power 20 or 22 or whatever? That you can only understand if you understand more about the mass of one atom. I hope this is clear. See you.